Welcome to the Deep Dive. We take your sources, dig in deep, and give you the insights you need to get up to speed fast. Today we're heading underground into a world that's vast, dark, really complex, and honestly incredibly difficult to document subterranean heritage sites.
Yeah, it's a tricky area. Think about caves with amazing prehistoric art. They're priceless, super fragile, but just mapping them accurately. Historically, that's been a huge challenge. We're talking massive costs, logistical headaches, just to get a decent 3D picture.
Exactly. And that's why this deep dive is so interesting. We're looking at a study that basically asks, can the LiDAR sensor in your pocket, in a modern smartphone, can it actually stand up to the professional gear archaeologists usually use? Can it make this kind of 3D mapping accessible to more people?
And the place they tested this, La Pileta Cave in Málaga, Spain. It's not just any cave. It's a really challenging environment. We're talking complex karstic systems, limestone caves carved by water, full of twists, turns, narrow bits.
And La Pileta itself is, well, it's profoundly important. It became a Spanish national monument way back in 1924. It has one of Europe's biggest collections of prehistoric art. Just incredible stuff.
It really is. The numbers are kind of staggering. 1,236 different motifs found so far. 872 Paleolithic, 364 post-Paleolithic. That's a history spanning something like 30,000 years.
Wow. 30,000 years.
Yeah. And it's not just paintings. They found unique things, too, like this ancient lamp with traces of Gravettian pigment. It's one of the oldest lamps ever found in Iberia.
Okay, so the mission for this research seems pretty clear then.
Right. Can this relatively cheap mobile LiDAR actually do the job? Can it reliably map these complex cave shapes and the art on the walls? Is it, a genuine shortcut for researchers who maybe don't have massive budgets?
Okay, before we get too excited about phones, let's just quickly touch on why this has always been so hard. Why the big investment traditionally?
Well, it boils down to the cave's shape, the morphology being incredibly complex, and just how hard it is to get to places inside. Think about setting up sensitive gear on wet, slippery, uneven floors in pitch darkness. It's tough. Often, traditional methods just couldn't get the fine detail, the spatial resolution needed for real scientific work, partly because the equipment itself is bulky.
And the gold standard for this has been TLS, right? Terrestrial laser scanning. What makes it the benchmark?
TLS gives you the highest fidelity, basically.
Yeah.
It generates these incredibly dense point clouds, millions and millions of 3D coordinates. And the accuracy, often down to the millimeter. So for this study, the TLS data was the ground truth, the benchmark everything else was compared against.
Millimeter precision sounds amazing, but I hear a but coming.
Oh, yeah. A big but, the cost.
Yeah.
The scanner itself, easily 20,000, maybe up to 80,000. And then you need specialist software. That's thousands more. Plus, the gear is big. You can't just squeeze it into tight passages. And its accuracy drops off with distance and the angle it hits the surface. So it has limitations.
Okay. I know there's another technique, structure from motion, SFM, using regular cameras. That's cheaper, isn't it?
SFM is definitely cheaper, yeah. And it can create really nice photorealistic models if you have good lighting and texture. But caves are its nightmare scenario. It needs to see distinct features in overlapping photos to work out the 3D shape. Dark, smooth, wet limestone often just doesn't have enough texture. Plus, the post-processing takes ages, and it often just fails in really dark areas.
Right. So that sets the stage perfectly for the potential game changer, the smartphone. Suddenly you've got consumer devices like Apple's Pro phones with LiDAR built right in, a 3D scanner in your pocket.
The cost difference is almost funny, isn't it? You go from potentially 80,000 plus down to maybe 1,000 or 1,600 for the phone,
Right.
And the apps for scanning. Some are free, some cost a few €100 maybe. It really does feel like it's democratizing the field.
And the immediate advantages seem obvious. It's super portable, easy to use, you don't need weeks of training, and you get a textured 3D model appearing right there on the screen in real time.
Yeah, but to make it work well in a tough place like La Paleta, the researchers had to get creative. They actually designed and 3D printed this special handheld rig. It held the phone steady, but also clamped on a couple of powerful rechargeable lanterns.
Ah, the lighting. Why was that so crucial if LiDAR uses its own laser light?
Because LiDAR captures the geometry, the shape. But for documenting the art, you need good texture, basically, good photos mapped onto that shape. They needed really strong, even light, about 2,000 lumens, but controlled so it wouldn't create harsh shadows or blow out the details on the rock surface.
It makes sense. So what's it actually like using the phone scanner down there in the dark? What are the catches?
Well, the big one is range. The phone's LiDAR only really works well up to about 5 meters. That's way shorter than the professional TLS gear.
5 meters. Okay, so you have to stay pretty close to the walls.
Exactly, and you have to move slowly. like really slowly, often in a kind of back and forth S pattern to cover everything. You also have to watch the screen constantly to avoid messing up the scan.
Messing it up how? What kind of artifacts?
Oh, all sorts of weird stuff you wouldn't get in a lab. Like bits of geometry floating in space if you accidentally scan your own arm or leg. Or reflections from water puddles or even dripping water can create false surfaces. And get this, even flying bats could apparently mess up the scan path if they flew through the laser beam at the wrong moment.
Bats. Okay, that definitely speaks to real-world fieldwork challenges.
Totally. It's not a clean room environment.
All right, so they took this setup, the phone, the custom rig, the lights, and put it head-to-head with the TLS in some really tricky parts of La Pileta. Which areas did they pick?
They chose a really demanding section. It included the Galleria de la Reina Mora, the entrance area of a big pit called the Gran Cima, and the famous Sala del Pez. That last one, the Room of the Fish, has this huge iconic painting called the Gran Pez, the Big Fish. So they were testing it on both complex spaces and specific art features.
Got it. And to be sure the comparison was fair, they first had to double-check the accuracy of the professional TLS itself, right?
Absolutely. Standard practice, they set up ground control points, GCP, throughout the test area. These are fixed points measured very precisely using a total station, like surveyors use.
Oh.
The TLS scan, which, by the way, captured over 1 billion points.
Wow.
Yeah, massive data set. They checked it against those GCPs, and it came out with a standard deviation of 19.6 millimeters.
Wow.
So really tight, confirming it was a solid benchmark. The alignment error between different scan positions was only 7 millimeters.
Benchmark confirmed. Okay, now the big reveal. How did the smartphone LiDAR actually compare when they measured its 3D model against that super accurate TLS data? This is the core question, right?
Which is the crux of it, yeah. They compared the phone's 3D mesh directly to the TLS point cloud, but only looking at the areas within that 5-meter range of the phone. And the headline result? The average deviation between the two, just 22 millimeters.
32 millimeters, less than an inch on average.
Yep.
Between a 1,000 euro phone and an 80,000 scanner, mapping that kind of complex 3D surface handheld in the dark. That sounds remarkably good.
It is remarkably good, considering, but, and it's an important but, you have to look at the standard deviation for the phone data too. That was 71 millimeters.
Okay, so 71 millimeter standard deviation. What does that mean practically?
It means, while the average difference is small, there are definitely points where the phone's measurement was further off from the TLS benchmark than that 22 millimeter average. There's more variability, more potential for larger errors in specific spots compared to the TLS.
Which makes sense given the hardware difference.
Exactly. The data is good, very usable, but you need to understand its precision limits. Oh, and for the detail-oriented folks listening, they did test several scanning apps. The one called Metascan seemed to give the best results when checked directly against the total station points with the lowest error.
Interesting detail. Okay, so let's talk practicalities. If the phone isn't quite as surgically precise as the TLS, what are its real advantages in the cave, beyond just the obvious cost saving?
This is where it gets really interesting. It comes down to maneuverability.
How so? TLS is on a tripod. Seems stable.
Stable, yes, but also stuck. Think about really narrow passages where you can barely squeeze through, or vertical shafts going up or down, or complex ceilings with lots of overhangs. TLS struggles massively there. The laser gets blocked. That's called occlusion. Setting up multiple scans to see around things is time-consuming and sometimes impossible.
I see.
But the phone, the operator, just carries it. They mentioned scanning tight squeezes, even scanning while suspended on a rope in a vertical shaft.
Wow, okay. That's access TLS could only dream of.
Precisely. No occlusions because the scanner is always moving with the person. You basically trade that last bit of pinpoint accuracy for the guarantee you can capture everything, every nook and cranny.
So it fills the gaps TLS leaves behind?
Exactly. And there's another big win for the phone, especially crucial for the rock art, the texture quality.
How is the phone's texture better?
TLS often has issues with lighting. The scanner's position relative to the light source can cause uneven illumination, shadows, or blown-out highlights on close surfaces. Parallax can be an issue too. But the mobile LiDAR approach, especially with those custom-mounted, bright, even lights they used, it produced much higher quality images mapped onto the 3D model. The visual appeal was better, and crucially, it makes it easier to actually see and locate the faint rock art or subtle geological details.
That visual clarity is key for archaeologists, absolutely. But we have to come back to that 5-meter range limit. That still sounds like a significant hurdle for mapping big spaces.
It is. It's the main operational constraint, no question. Mapping a large chamber means doing multiple, slow, careful passes. And there was another interesting finding about accuracy. The study found the biggest deviations, the largest errors in the phone data, tended to happen on the smoothest parts of the cave walls.
Wait, smooth surfaces were harder for the phone, not rough ones. That seems counterintuitive.
It does it first? Yeah. But think about it. When the surface is very smooth, lacks bumps and features, the LiDAR has fewer unique points to lock onto to figure out the 3D shape accurately. Conversely, the very uneven, bumpy, undulating surfaces common in these karstic caves actually gave the phone more distinct geometry to work with, helping it maintain its accuracy better.
Huh. So the very nature of the cave environment kind of played to the smartphone's strengths in a weird way.
In a way, yeah. For this specific kind of complex morphology, it performs surprisingly well.
So wrapping this up, what's the big picture for documenting caves going forward? Is it goodbye to the expensive TLS?
No, not at all. The clear recommendation coming out of this research is an integrated approach, a combination of both technologies.
Okay. How does that work?
You use the TLS for what it's best at, establishing the overall high-accuracy framework, capturing large distances across big chambers, providing that rock-solid geometric base. Then you bring in the smartphone LiDAR for its strengths, getting into all the tight, inaccessible spots the TLS can't reach, capturing that superior texture detail, especially for the art, and filling in all the gaps. Together, they give you the most complete, comprehensive, and accurate picture of the entire cave system.
That sounds like a really smart way to leverage the best of both worlds. It means even research groups with smaller budgets can still get really valuable, spatially accurate data.
Absolutely. The smartphone provides genuinely reliable geometric models. These as-posed digital twins are crucial for preservation, for future analysis like studying the shapes of paintings digitally, and, importantly for you listening, it makes these incredible, hidden underground worlds ready for virtual reality. It opens them up for virtual exploration by anyone, anywhere.
It really is amazing how fast this tech is moving and changing how we study these places, moving from rough sketches to data-driven models.
It is. And that shift brings up a really interesting final thought for you to ponder. For centuries, our understanding of these sites relied partly on hand-drawn maps, right? Filtered through the skill, the eye, maybe even the artistic interpretation of the person drawing it. Now, remote sensing, like smartphone LiDAR, offers this objective, data-driven precision. So the question is, what do we gain with this absolute technical fidelity? And is there anything potentially valuable, maybe a certain kind of human insight or interpretation, that gets lost when the art of the map is replaced entirely by the science of the data?